This is the Matanuska Glacier in Alaska. It really is one of the most astonishing places I've ever seen. And this whole landscape is testament to the erosive power of this stuff, this mixture of ice and rock as it rolls down this valley over hundreds of thousands of years and creates this astonishing landscape. But the reason it can do that is because of the delicate balance of the Earth's atmosphere. See, our planet is just at the right temperature and pressure to allow water to exist as solid, as liquid, and as gas, as vapour in the clouds. And so the sun can heat up the oceans and it can move the water over to the top of the mountains. It can fall as rain, turn to ice, become a glacier, and then sweep down the valley to sculpt this astonishing landscape. Just as our atmosphere allows all this to exist, the atmosphere of Titan is the perfect temperature and pressure to allow something to exist that has never been seen before on a world beyond Earth. This is a picture taken of the South Pole of Titan by Cassini in June 2005, and it's subsequently become one of the most important and fascinating pictures in the history of space exploration. The interesting thing is this black blob here. Now this fascinated the Cassini scientists, but the explanation as to what that is had to wait just over a year till July 2006 when this picture was taken. And it's a radar image, this time of the North Pole of Titan. And you see again these huge black areas. But black in this case means that the radar waves that bounced onto them didn't come back, so they're completely black. And there's only one really good explanation for that. That is that they're incredibly flat surfaces. In fact, they're surfaces of liquid. So this picture combined with this picture means that this is the first observation of a liquid, a lake, on the surface of a body other than the Earth in the solar system. But these lakes, of course, cannot be lakes of liquid water because the surface temperature on Titan is minus 180 degrees Celsius. And at those temperatures, water is frozen as hard as steel. So, if these are not lakes of water, then what are they? I've come to Cape Town in South Africa to do something that I have always wanted to do, but I never thought I'd get the chance. I'm about to fly incredibly high, to the very edge of the Earth's atmosphere. From here, I'm hoping to see something that only a handful of people have ever seen. The thin blue line, the fragile strip of gas that surrounds our whole planet. And this is what's going to take me there. So this is an English Electric Lightning, the most beautiful fighter aircraft ever built. This is when England built the best aircraft in the world. The Lightning is no longer in service, but this piece of magnificently overpowered engineering is going to take me 18 kilometres straight up. Actually, I read somewhere that when you read about the altitude of the Lightning, it says altitude estimated 60,000 feet, ceiling classified. So don't know how high these can go. I've heard rumours they can go to 80,000 feet, which is amazing.
My journey will take me beyond almost all the molecules of gas that make up our atmosphere.
If you feel you're gonna get sick,
Yeah,
use a bag, okay?
right. Hopefully not.
To get there, I'm going to experience what made the lightning famous: vertical takeoff. It takes just seconds to reach 9 kilometres up, but I'm still in the thickest layer of the atmosphere called the troposphere. But the further I climb, the thinner the atmosphere becomes.
Up at 58,000 feet. 90% of the atmosphere is below me. The only people above me are on the space station. So beautiful.
I'm now at 60,000 feet, 18 kilometres up, and the highest I can go. Above me, the sky is a deep, dark blue. And that is what I've come to see, our atmosphere.
That really is the thin blue line that protects us. So fragile and so tenuous. Just a tiny sliver of blue. Amazing.
In these alligator-infested backwoods, the final piece in the puzzle of Einstein's universe is being put to the test. This place stands at the leading edge of the exploration of gravity.
Really what we want to do here
Joe Giami is the head man.
Gravity will probably and hopefully confuse us for a long time before we figure out what it really is. And scientists are happy when they're confused and hot on the trail of something fun.
This is the Laser Interferometer Gravitational Wave Observatory, or LIGO for short.
Any signal we see is going to be from something really, really interesting and cool. Data from those kinds of sources would be really valuable to learn things about gravity and the nature of gravity.
This machine was built as an observatory, a chance to witness violent galactic events beyond anything we've ever seen before.
One of the things I hope to see is when you get two stars called neutron stars. Now, a neutron star is probably twice or 3 times as heavy as the sun, but compressed into a ball about 10 kilometres across, so the size of a city. And there are places where there can be 2 of those things orbiting around each other at about 100 or even 1,000 times a second.
The incredibly dense neutron stars spin round each other, churning up the space-time. As they spiral in, going faster and faster, Einstein predicts this sort of violent cosmic event will create something called gravitational waves. But what exactly is a gravitational wave? It's not that easy to describe. If a wave came through this room, it'd... what did I say? Ripples in. space-time isn't just something that's, you know, up there amongst the stars. It's here, right? It's in front of me and it's inside me. So when I move, I disturb it. I send out ripples in it. It's just like if I jump into a swimming pool and start swimming, I'll send out ripples on the surface of the water. It's the same with space-time. In theory, these waves would cause space and time to stretch and shrink as they pass through the universe. These waves are physical distortions in our reality. You know, they really are stretching and contracting the space and the time that we're in. But trying to see these gravitational waves using the LIGO machine is proving very difficult.
Gravity waves cause lengths to change in one direction differently than the other direction. So if I were very stretchy and a gravitational wave were going through me, this is what would happen. I would get shorter one way and longer the other way.
The machine works by using a laser beam to measure the distance between two sets of mirrors suspended at the ends of the two 4-kilometer-long tubes.
So from up here you can see pretty much all the key components. You can see running off to the right there and also running down under our feet are tubes that carry the light to the end stations. So there's a mirror here and there's a mirror 4 kilometers over that way. And when the gravity wave comes through, the distance between those mirrors changes.
They're basically just fancy rulers.
That's right, that's right.
But even after 5 years in continuous operation, the team hasn't been able to observe any violent gravitational hotspots. This is because they still haven't detected Einstein's elusive gravitational waves.
This is one piece of nature we haven't really observed right yet, to see gravitational waves, whether they really affect things here the way we think they do. We don't know where the sources are that we're looking for, so we have to look farther and farther out.
If we can figure out how gravity works at the level of the smallest subatomic particles, then maybe we can finish what Newton and Einstein started and form a complete picture of this mysterious force of gravity. To achieve this goal, we have to try to recreate the conditions of the Big Bang here on Earth and peer deep into the heart of the subatomic world. This place is Fermilab, and I used to work here. It's home to the Tevatron particle accelerator. The Tevatron basically works by bashing stuff together and seeing what comes out. What we do is we take protons and we accelerate them around that way, and antimatter protons, send them around that way, and they pass by here 50,000 times a second, very close to the speed of light. And then we collide them together, we smash them together. It's through collisions like these that the nature of matter has been revealed. But the force of gravity still sits outside what we know. One of the ways we might get to the truth about gravity is to try and fit it into the beautiful framework we have that describes the subatomic world. Quantum mechanics predicts that the force of gravity should be transmitted by a particle. We've called this particle the graviton. If we could just find these gravitons, then we might at last arrive at a quantum theory of gravity, a universal theory that will work everywhere in the cosmos. For 8 years, Greg Landsberg has been using Fermilab's particle accelerator to try to create gravitons.
These particles, well, we haven't quite seen them, so what I'm telling you is we
Haven't
just,
quite seen them.
That's right, it's our hypothesis, so we don't quite know if this is true or not. it's not that we can shine light on gravitons to see them. So we have to find some other means. It's amazing that the way to see the graviton is by not observing it, by observing it's missing.
To see something that's missing, Greg is effectively looking for missing energy. Typically, when you batch things together, the energy of the original particles should be the same as the total energy of all the particles coming out.
But if you were to make a graviton in that collision, then our detectors are certainly not capable of seeing it. So the graviton will take energy away from the collision. Energy will appear to disappear. So the old D0 control room, I've been here for years.
So what this picture tells us, it's called event display. The height of these bars is how much energy is released in this collision in that particular direction.
So you've got a collision in the middle there, and
Right.
there's stuff spraying out.
And so what we're trying to do is to sum all this energy to see if something is missing. If you look at this display, you see a lot of energy going in this direction, but very little on the other side. And this yellow bar, in fact, represents the fraction of energy which is missing.
All right, so if you see that, that means there's something escaped.
That's right.
If gravitons are created, Greg believes the reason why they would disappear is because they vanish into a place beyond our reality, into some sort of extra dimension.
Now we're all familiar with the three dimensions of our world, as up and down and north and south and east and west. But what scientists like Greg are proposing is that there can be extra, hidden, unseen dimensions. It sounds ridiculous, and it is impossible to picture, but theoretically it's possible. And it's also possible that gravitons, the particles of gravity, can spend most of their time in those extra dimensions.
If gravitons really are created and they escape in these extra dimensions, we would never see them. So although it might sound like a very odd hypothesis, an odd concept, really nothing prevents us of thinking in this direction, especially if we can solve these mysteries.
Newton could predict the effects of gravity. Einstein worked out why it exists. But by finding a graviton, we might at last truly understand gravity.
I tend to think of exploration as walking across new terrain and planting a flag, like the polar explorers of old. But it doesn't have to be that. It can also be intellectual. And actually, for most of history, our exploration of the universe beyond Earth has not been physical. It's been looking up at the stars.
These are the Atlas Mountains in North Africa. According to Roman legend, they held the heavens above the earth. And they are one of the finest places to come to view the stars. From a place like this, it's easy to appreciate the profound effect that the night sky would have had on our ancestors.
You know, from a modern perspective, astronomy can seem remote and arcane because we've lost our connection with the night sky. From a city, you just don't see a sky look anything like this. From the darkness of the Atlas Mountains, it's really, truly majestic.
So for our ancestors, the connection with the night sky would have been incredibly intimate. They looked into the skies to understand their place in creation, and the movement of the stars told them one thing. They were at the center of the universe.
Up there is Polaris, the North Star, and it's almost exactly aligned with the Earth's spin axis, which means that as the Earth rotates, all the stars rotate through the sky around that point.
So it looks for all the world as if the Earth is at the centre of the universe and the stars rotate around it. And that's of course what the ancients thought for thousands of years. And why not? Because it's obvious. But wrong. To understand the Earth's real position in the solar system, we need to look at the one set of bodies that doesn't behave as predictably as the stars. Well, understanding the retrograde motion of Mars didn't come easy. That's why it took over 2,000 years to work out. But I'm going to explain it using a stick and some rocks. The key thing is that the Earth is not at the centre of the solar system. The Sun is. And the Earth and Mars go around it in almost circular orbits. So when Mars is viewed from the Earth, then it's seen on the sky. In fact, on the constellations of the zodiac. So as Mars orbits around and the Earth orbits around, then from that position, Mars will look like it's there on the sky. Mars moves and the Earth moves in that position, and Mars moves in that direction across the sky, and again in that position, Mars will be here. So you see it's moving in a straight line across the sky. But what happens when the Earth overtakes Mars? Then, look at the line of sight. Mars has moved back to there. It's reversed its direction, and it continues to do that until the Earth gets round to somewhere like there, and Mars is here, and then you see the line of sight means that it started moving that way again. So Mars has executed that strange looping motion on the sky because the Earth overtook Mars on the inside, and that's why the retrograde motion happens. Simple. Understanding the retrograde loops was one of the major achievements of early astronomy. It created the concept of the solar system and allowed us to build the first accurate maps of the planets and their orbits around the Sun. I think most people thought that we would be back to the moon quite soon. Actually, it's been 50 years and we haven't gone back. But now we're trying to reacquire those skills because we want to go further. So the next step is Mars. Mars is in our backyard. It's the most Earth-like place in the solar system other than the Earth, but by a long way. It's almost habitable. So I think if there is going to be a new frontier physically that we're going to explore, then there is no choice. It has to be Mars. NASA is developing machines for mining and building on other worlds. The moon is seen as a stepping stone to Mars. One day, robots will mine the lunar surface to build habitats for human settlers.
One stick drives one side of the wheels and the other stick drives the other side of the wheel.
Robotics engineer AJ Nick is letting me take one out for a spin.
So we turn on this button and you can go ahead and raise this arm over here and keep driving.
You know, there's a real feeling of stability there, and you're confident I can't break this.
I have done way worse to this robot.
I suppose the obvious question is, if you want to mine this, why don't you just get a shovel and dig it up? Why is the robot so complicated?
The first problem is we're trying to make everything as lightweight as possible, fit inside of a rocket. Then you get there on the lunar surface, and you have reduced gravity once you get there. So now the thing that was already really light, because you had to make it light to fit in the rocket, is even lighter while it's there on Earth. Since we don't have a lot of weight, it's very difficult.
AJ and his team have come up with a unique design that will allow their robots to work in the moon's weak gravity. So now I'm digging. The scooping drums at either end rotate in opposite directions. This has the effect of pinning the robot to the ground, allowing it to dig without floating off into space.
As one drum on the front is digging, the other drum is rotating the opposite direction from the other drum. And so that allows the excavation forces to be canceled as it's digging.
This is the only vehicle in the world that can dig more than its own weight. If I took it into this trench the wrong way,
right,
it may well fall over. Can I do that?
Yeah.
Oh, yep. Unlike other planetary rovers, these robots are meant to be robust, designed to get themselves out of problems, even if they're flipped upside down. But it's really easy to drive and really manoeuvrable and really powerful, and it does seem like you can get out of a lot of trouble. Once the lunar dirt has been dug up, it needs to be transformed into a building material.
Show you some materials here.
Senior technologist Robert Muller has been sintering the lunar dust, heating it until it solidifies.
So the result, a well-sintered regolith, is this. And that's essentially turning crushed rock back into solid rock.
That's really quite heavy, actually. That feels quite dense. So that is just this material in an oven, essentially.
That's right.
By mixing the regolith with plastic, Rob can create something far more versatile, a material which can be used in a 3D printer.
And we use the big robot arm. We have a print head on it. And then we're able to make objects like this. This is a blast deflection wall, or this is an ogive dome. It could be used for the roof of a habitat when it gets really big. And in fact, it's quite strong. If you look down at it, it's very strong. You can kick it all day long and it won't break.
That's quite... So that is built by that robot?
Yes.
Using essentially the regolith that you would find on the moon?
That's correct. So you never bring any materials from Earth.
Yeah.
You go mine them on the moon, and then you build whatever you need to create your local moon base out of local materials. All you have to bring is the robot.
Everything is there, is the point.
Everything is there. The only two things are missing are technologies and imagination. If we can put those two things together and harness the materials and the energy we have in space, we have all the resources in space we need. We just need to be clever enough to learn how to use them.
Floating in the Sea of Cortez off the coast of Mexico is the research vessel Atlantis, the mothership for the exploration of one of the most alien worlds we know. But it's an alien world on our planet. The Atlantis is the launch vessel for Alvin, one of the world's most rugged submarines. Built like a spacecraft, it's designed to explore the deepest depths of the ocean. And I'm lucky enough to have hitched a ride down to the sea floor, 2 kilometers beneath the surface.
It's honestly got to be the closest thing to going into space that you can do. And given that I'm not going to go into space anytime soon, I think this is the next best thing. See you in 8 hours.
Starboard time!
The parallels to spaceflight are obvious. As the tiny capsule descends, we're leaving the familiar world of the surface of our planet and entering a strange, hostile world.
240 reading, 400 meters.
If anything goes wrong, we will be completely on our own. It's very rare that you get to do something so challenging and so alien. To be taken to that environment in the very deep ocean, it's strange and silent and unusual. And it's tiny as well. So there's three people crammed into this little titanium ball, which kind of creaks a bit as it goes down. Creeping's never good. At the Earth's surface, we're used to one atmosphere of pressure. As we descend, the pressure increases by another atmosphere every 10 meters, and it soon adds up.
You're gonna have to repeat that if you want to be
So we're just approaching a kilometre deep. The pressure outside there is now, what, 100 atmospheres? That's higher than the atmospheric pressure on the surface of Venus. Without knowing, if you were asked the question, could life exist down here, 100 atmospheres, cold, dark, no sign of sunlight at all, it's pitch black there, you would say no. Well, I would say no. For me, the fascinating thing about finding life down here is that the conditions on the deep ocean floor are more similar in many ways to the conditions on worlds hundreds of millions of kilometres away out there in the solar system than they are to the conditions just 2 kilometres above my head on the Earth's surface. You know, it's incredibly dark, there's no sunlight, there's a brutal mixture of hot and cold water and just, well, rock and minerals. So if life can not only survive but even flourish in these conditions, then you've got to feel that it's much more likely that life can also survive and flourish out there in the solar system. One of the main benefits, I think, in looking at life in extreme environments on Earth, so-called extremophiles, is that you get a wider view of what life is and what chemical elements or compounds it produces. And that is useful because really, if you think about life subsurface on Mars, for example, if it exists, we really don't know how that life would behave. If you're interested in astronomy and SETI, the search for extraterrestrial intelligence, you know the name Frank Drake. And when you meet someone like that, one of your heroes, it's a special moment. And he did not disappoint. So if I'd have asked you back in the 1960s, by the 21st century, do you expect to have seen a signal? What would you have said?
I would have said, yes, I expect to succeed, because we were doing a lot of searching then.
Does that make you disappointed?
I'm disappointed, yes, but not surprised. What we've learned over the years is that the searching has to be much more comprehensive than we realized 50 years ago. But we know it's still doable. It just takes much more time than we imagined. Let me show you something. This is an orchid, a very peculiar and beautiful orchid. It's very fragrant, which actually only blooms 2 days a year. If you had been here 2 days ago, you wouldn't have seen this orchid, and you might have thought that this plant never blooms. Well, so it is with SETI. We've learned that we must search over and over and over through the years till we are in the right place at the right time to make the discovery.
What are they called?
This is called a stanhopea. It has hope in its name, and we have hope that someday we'll be in the right place at the right time in SETI.
Frank Drake makes the argument that if there are civilizations out there, then you might imagine that the radio waves that they send out are passing through the galaxy. And so they would be passing through this room now. So if only you had a sensitive enough detector, then maybe you could pick up the signals And he's right. The point he's making it as a scientist is that the only way you're going to know is to look. And he doesn't think we've looked closely enough. And I agree with him. But Frank wasn't content just to hang on the line, waiting for ET's call. In 1961, he devised what remains a useful scientific framework for considering how likely it is that we share the galaxy with others. The Drake equation has become famous because it gives us a tool to continue the search. It dares us to answer a series of provocative scientific questions. And on the left-hand side, there's the number we want to measure, the number of intelligent civilizations in the galaxy that we can communicate with. And then there's this group of terms that really ask questions about ourselves. How likely is it for life to arise on a planet? How special is the Earth? How special is the Sun? How special is the solar system? How special is intelligence? And then there's this last term, L, which perhaps speaks to us most profoundly of all, the lifetime of intelligent civilizations. Do civilizations live for a long or short time? And if it's short, what is it that destroys them? Is it a natural disaster? We do, after all, live in a violent universe. Or are they condemned to destroy themselves? When Frank first thought about it, sort of 50 years ago, for example, the number of planets around distant stars, how likely is it? What's the probability that a star will have planets around it? We didn't know. We hadn't detected any. It's not till the 1990s that we have the evidence for planets around different distant stars. Now we have dedicated missions to go and look for them. And these missions are revealing a universe full of possibilities. And in the constellation of Pegasus, around a sun-like star, there's a planet called Osiris. It's way closer to its parent star than Mercury is to our sun, but it's a massive gas giant, a hot Jupiter. And by measuring the light that shines through its atmosphere, we found that the atmosphere is full of hydrogen and methane and water. And just 24 light years away in the constellation of Scorpius, there's a small rocky world, one of the most Earth-like worlds we know. It orbits around a red dwarf star, which is one of 3 stars in the system. A planet with 3 suns in the sky. This is Varanasi. For Hindus, it's one of the holiest sites in all of India. Part of what makes it so special is the orientation of its sacred river as it flows past the city. This is the one place on the Ganges where you can bathe in the river on this shore and you can see the sunrise on the eastern shore. It's the only place where the Ganges turns around to the north, so you can do that. When the sun rises tomorrow, a truly extraordinary phenomenon will take place, a total eclipse of the sun. It's an auspicious occasion for a place that ancient Hindus knew as the solar city. Science is different to all the other systems of thought, the belief systems that have been practiced in this city for millennia, because you don't need faith in it, you can check that it works. So, for example, I can tell you that tomorrow morning at precisely 6:24 a.m. the moon will cover the face of the sun and there will be a total solar eclipse. I could tell you that in 2904 there will be 5 solar eclipses on the Earth. And I could tell you that on July 16, 2186, there will be the longest solar eclipse for 5,000 years, 7 minutes. However, as anyone who's been to India in June, July will know, the climate is not entirely predictable, right? It's a cloudy, rainy place. And so we took a huge gamble. It's 5:28, so that's time of first contact, and you
You can't see the disk of the sun at the moment. It's obscured by low cloud. The edge of the moon is at this point just beginning to touch the disk of the sun. You can see the sun emerging through the clouds. See the disk. Oh, and you can see the moon. Can you see the moon on the top? Oh yeah. It just vanished. You can see the limb of the moon there. Absolutely fantastic. Yeah. See the sun? You can see the celestial mechanics, the clockwork of the solar system at work. The alignment is absolutely perfect. Oh, there. Look at that. You know, if you ever needed convincing that we live in a solar system, that we are on a ball of rock orbiting around the sun with other balls of rock, then look at that. That's the solar system coming down and grabbing you by the throat.
It's one of the most remarkable things I've ever experienced, because this piece of rock went across the face of the sun on time, to the second, exactly as had been predicted using Newton's laws. And I got this feeling that I'm on a piece of rock in space. And it was this totally unexpected feeling.
Look at that!
Why does everything fall to the ground at exactly the same rate? Well, that actually is a clue that there's something much more interesting about gravity than just a force between things. It took the genius of Einstein, who started thinking about gravity 200 years after Newton, to realise that the way things fall is telling us something profound about the nature of reality itself. He realised that when things are falling, you could see that they're not falling at all, because they're all staying in the same place relative to each other. So it led him to his theory of relativity. And so we thought, well, what better way to introduce Einstein's theory than to go and film that in action? There is a place where you can see with your eyes what Einstein saw in his mind.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left.
Galileo's observation that all objects fall at the same rate is correct, but it's far from obvious.
In this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see
the true nature of gravity, we have to remove the air.
Dropped 2 millitorr in the last 30 minutes.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exact. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
Your background is silent.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just... you know, and then we all realise, you go, we're applauding a force of nature. So why are we doing that? We all knew what was going to happen, but it was so wonderful to see it.
Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.